In this video, we're going to be using the Helix Wave Generator software that I showed you a few videos back to help demystify the idea of the polarization of light and indirectly Maxwell's plane wave, which you can see right here. And this, of course, involves complex numbers, which we have been talking about extensively over the past few videos. And so I believe this is the most important concept to understand both mathematically and in terms of physics, okay? And so in the version of complex numbers that I'm promoting, the complex number a plus bi is a 2 by 2 matrix with the A on the forward diagonal and the B on the backward diagonal. As a companion to this, we have the 2 by 2 matrix with the cosine on the forward diagonal and the sine on the backward diagonal, and the cosine has the same sense, usually positive, and the backward diagonal has the opposite sense. If this is positive, this is negative, and if this is negative, this is positive. And this corresponds to Euler's formula, cosine of theta plus I sine of theta, where theta is the phase of the wave. And as I showed you in previous software, this is what I use to generate the helix wave. Okay, so this is what I use to generate the helix wave. So this version of the generalized version of the complex number I actually use to generate the Mandelbrot fractal. Okay, so I use this to generate the Mandelbrot fractal, and I use this to generate the helix wave. So we're going to start by demystifying the polarization of light using the software I developed for the helix wave interference that I showed you a few videos back. So here is the code for generating the helix wave. On the right here, of course, you can see the helix wave as it's being generated. This is basically the same code as what I showed you before, only now instead of having two waves going in opposite directions and interfering with each other, I have two waves going in the same direction and interfering with each other. And so here we have I'm calling it wave 1, the red wave, and now I'm going to draw the blue wave, and you can see that it is propagating in the same direction and the circle is moving counterclockwise. So when I draw the red wave, okay, you see the same thing. This circle is being drawn in the same direction, and this is the way that the wave is being generated, and it is propagating from left to right. So now I have two waves. I'm going to draw them both. I have two waves propagating in the same direction. Okay, when you look from the back, you can see the red. When you look from the front, you can see the blue, and they are propagating in the same direction. But today we're not going to be talking about interference patterns, so we're going to make that go away. And what we're actually going to talk about are electromagnetic waves, which are complex. Okay, so the electric component and magnetic component of the electromagnetic wave is propagating in the same direction. Okay, and so this is what we're going to get to. This is the point we're going to make eventually, but first we're going to talk about polarization of light. And we are going to be using this same code to mimic the polarization, the elliptical polarization of light and the linear polarization of light. The first thing we need to talk about is circular polarized light, because this turns out to actually be the trivial case. The circular polarized wave as depicted in this image here is in fact the helix wave that I implemented in my code. It is exactly the same. The dynamics is the same. The wave is propagating in the same direction as in this wave here. And the the sphere that I am drawing is moving in the same direction as the arrow in this image. And so this is in fact exactly the implementation of the helix wave is in fact an implementation of circular polarized light. So here is the code that I'm using to draw the red wave. Okay, this is draw wave 1, And when we come down here, you will see that this is currently being driven by this rotation matrix here. Okay, this rotation matrix with the cosine of the phase of the wave on the forward diagonal and the sine of the phase of the wave on the backward diagonal. The cosine, both cosines are positive, and the sines are positive and negative. Okay, so when you use this transformation matrix, you get the helix wave, you get the circular polarization, what is commonly called circular polarization of an electromagnetic wave. So what I have done here is I have generated a whole bunch of rotation matrices that we're going to override this rotation matrix with, okay? And doing that, we're going to see how we can use the 2x2 matrix version of Euler's formula to generate the elliptical and linear polarizations of light. The polarizations generally look like this on a graph, okay? So sometime when you have elliptical polarization, you see sort of an oval pointing either to the right or to the left. And you will see also, depending on what parameters we use, you will see something that looks more like a line. So this would be linear polarization here, and this would be elliptical polarization here, and this would be circular polarization here. So in this rotation matrix here, I have implemented something called a phase offset. So normally when you're doing circular motion, the phase is the same in both the cosine and the sine. So the phase is the same in all of the matrix entries. So what we're going to do is we're going to allow for different phases in the cosine term and the sine term. And to do that, I've implemented a slider bar down here, and you'll see what happens when I enable this code. So when I enable this matrix down here and rerun my code, then you're going to see exactly the same thing as you saw before, only now I'm going to be moving the slider bar, and when I do, I'm going to be increasing and decreasing this phase offset. Okay, so here is what happens when I do that. Okay, here you can see that we're getting the elliptical shape that we saw in the definition of elliptical polarization. Okay, and then when I go the other way, you will see we get the elliptical polarization in the other direction, as you see here. Okay, also, if I go further, so that's say around 45 degrees. When I go to, so I'm going to go to plus 45 degrees, and you see that this is basically 45 degree on a 45 degree angle. And then I'm going to go to plus 90. I'm going to go to exactly 90. Okay, that's pretty close. There's 90. And there you see the line. So you see we are looking at the helix wave from this side, and that corresponds to these two polarizations. Okay, and so the wave is coming towards me, so I am not seeing the wave until I tilt it like that. And now I can see that we have a sine slash cosine like wave that is propagating towards you, but it is now linear polarized. Okay, so now if I go to the other side, if I go to minus 90, you're going to see the linear polarization in the opposite direction. And so the main thing to notice here is that something special happens at minus 90 and 90. Okay, at minus 90 and 90, what you are seeing is perfectly linear polarized light. Okay, you're seeing perfectly linear polarized light where the light is, let me get this right to 90 as perfectly as I can. Okay, where the wave is really in a plane. Okay, so this is the planar wave of Maxwell's equations. Okay, this is a plane wave. It's a wave that's propagating in a plane. This is linear polarized planar wave. And I was able to implement it by modifying one of the phases, the phase in the sine term of Euler's 2x2 matrix. Okay, all I did was modify the phase. I incremented the phase by 90 degrees. So this is 90 degrees out of phase, I guess, with the cosine wave. And when that happens, you end up with a plane wave. So the next thing we're going to do is we're going to apply this phase offset from the slider bar to the cosine term on the forward diagonal instead of the sine term on the backward diagonal. Okay, so here is what we get. We start out similar to before, only now when I go towards positive 90, the ellipse is angulated to the right, and when I go to minus 90, it goes to the left. Whereas with the previous one, let's just go to back to the previous one quickly, right? In this one, when I go to positive, when I go in the positive direction, the ellipse is to the left, and when I go in the negative direction, the ellipse is to the right. Okay, so I'm running the same code. I'm doing exactly the same thing as I did before. Okay, I'm going to run this, and so you see the ellipse. They're just going in the opposite directions, but you get the same thing happening at plus 90 and minus 90. You get the linear polarization, okay, which we can look at in 3D. You can see that it is, in fact, a plane wave. It is a linear polarization of the helix wave, of the original helix wave. So the next thing I'm going to do is I'm going to ignore the backward diagonal. So I'm going to ignore the sine terms, which is kind of like ignoring the imaginary component of the complex numbers. Now, as I said earlier, complex numbers are, electromagnetic waves are complex and can be described by complex numbers. And this is the formula I use, the 2x2 matrix version of Euler's formula, to mimic an electromagnetic wave. And this is what I am doing in this video. Okay, so I'm going to set I'm going to hard code the sine term to 0. And then I'm going to leave the cosine term as it is. Okay, so let's see what happens here. Okay, so now what I have is what is referred to as vertical polarization. Okay, so what I have is the same linear polarization, only I have forced it into the vertical orientation. And so in the literature, this is referred to as vertical polarization, and I am able to mimic that by setting the sine term, the backward diagonal, to exactly 0. But I don't really like the idea of hard coding, putting a 0 into this 2x2 matrix, because this is Euler's formula, and Euler's formula is cos of some angle plus I sine of some angle. So I want the backward diagonal to still have a sine, and of course if I want that value to end up being 0, then I can plug in the sine of 0 into the backward diagonal, and I get exactly the same effect. Okay, so if I want to keep the sign in the language in the matrix, then I just go sine of 0, because the sine of 0 is 0, and I get my nice vertical polarized plane wave. So next what we're going to do is we're going to generate the blue wave. Now this, I'm assuming, is the electro part of the electromagnetic wave. Okay, so this is what we would normally be drawing as the electro part of the electromagnetic wave. And so what we have done is we have set the imaginary component, the backward diagonal, to 0. Now so the assumption here, at least my assumption in the logic that I'm using, is that the forward diagonal corresponds to the electro part of the electromagnetic wave, and the backward diagonal corresponds to the magneto part of the electromagnetic wave. Okay, so this is my line of thinking, this is my hypothesis, that if an electromagnetic wave is complex, okay, if the parameters for the electromagnetic wave are complex, then the forward diagonal contains all the information for the electro part, And the backward diagonal contains all the information for the magneto part. And now here the magneto part was set equal to 0. Okay, so this is the language that I'm using to talk about electromagnetic waves in terms of complex numbers and the 2 by 2 matrix version of Euler's formula. Okay, so I'm going to go up here and I am going to disable the red wave, excuse me, and I'm going to draw the blue wave. Okay, so now we're back where we started. Now we have a helix wave, but it is now blue, and now what we're going to do is we're going to work on the magneto component of the electromagnetic wave. Okay, so let's go down to draw wave 2, which is the blue wave. And right now we are running the standard Euler's formula in 2 by 2 matrix form, excuse me, where the phase on the forward diagonal in the cosine terms is the same as the phase in the backward diagonal sine terms. So we can assume that all of the elliptical and linear polarizations from the red wave work the same on this helix wave, because it is the exact same helix wave as I was drawing before. Only now what we're going to do is we're going to hard code the cosine term to 0 instead of the sine term. Okay, so now instead of making the sine equal to 0, I'm going to make the cosine equal to 0. Okay, and I'm going to run this. So when we do that, what we discover is we get horizontal polarized light. Okay, so we get the horizontal component of the electromagnetic wave under linear polarization. Okay, so as you can see here, this is a plane wave, and it defaults to the horizontal orientation. And so this is, I'm assuming, is the magneto part of the electromagnetic wave. Okay, earlier we had developed a red wave that had vertical polarization, linear polarization. This has horizontal linear polarization. The vertical and horizontal are 90 degrees out of phase with each other in space. Okay, so next what I'm going to do is I'm going to display both of these waves at the same time. Okay, so I'm going to uncomment that, and now we can see both waves. Okay, so we can see that we have the vertical polarized electro component of the wave, and then we have the magneto polarized, linear polarized, horizontal linear polarized magneto. So electro, magneto, and as you can see, they are 90 degrees orthogonal to each other in space, but there's a problem. Okay, so you can see that although they are 90 degrees orthogonal to each other in space, they're also 90 degrees orthogonal to each other in time. This is not the same as what we find with Maxwell's equations, with Maxwell's derivation of the plane wave, where the magnetic field and the electric field are in phase in time. They are 90 degrees orthogonal to each other in space, but they're in phase in time. Okay, so let's see if we can make that happen in my code. So looking at this here, we see that we set the cosine term to 0, but I don't really want a 0 term in my matrix. I would prefer that we put that back to a cosine term. And so the cosine of the cosine of pi over 2 is equal to 0. So I can replace the 0 with a cosine of pi over 2 on these two entries, and we will end up with the same result. Okay, we'll end up with the same result. We still have this out of phase problem though, but if I set my phase offset to 90, my extra phase to 90, then these two phases become in phase in time. Okay, so I'm going to do one more thing here, because it seems that if I set this phase offset to pi over 2, so instead of making it a variable, I'm going to set that to exactly pi over 2. which is what I'm going to do right here. So I'm just going to create a shift parameter, a shift variable called pi over 2, and I'm going to set the cosine terms to pi over 2, and I'm going to set the sine term to the phase plus the hard-coded phase shift of pi over 2, and then you will see that we now have the electro component and the magneto component in phase in time, but out of phase in space. And you can see that where these two spheres are intersecting each other, they are in phase. So the main point of this exercise was to show you how I was able to derive Maxwell's plane waves, regardless of whether they mimic reality or not. Okay, I was able to mimic the plane waves. I was able to derive the plane waves and visualize them using the 2x2 matrix version of Euler's formula and variations thereof. Now, the thing that bothers me about this derivation is that in order to get the electric wave and the magnetic wave, the electric component and the magnetic component, for the electric component, I had to set the backward diagonal to 0. And for the magneto component of the wave, I had to set the cosine term in the matrix to 0. And so that bothers me a little bit. It bothers me a little bit because I know in reality that is what they've done. I know with Maxwell's plane wave derivation that at some point in the derivation they ignore the imaginary component, okay? And so I'm not really sure why. So what I did was I asked ChatGPT. Okay, so this is me asking the question, in the derivation of Maxwell's equations, why did they ignore the imaginary component of the complex number? And so ChatGPT answers, in the derivation of Maxwell's equations, the use of complex numbers is primarily a mathematical tool to simplify the equations and handle oscillatory phenomenon, particularly in the context of electromagnetic waves. When dealing with time-varying electromagnetic fields, it is common to represent them using complex numbers due to their convenient mathematical properties. In Maxwell's equations, the time-varying electric and magnetic field are often expressed as complex quantities, where the real part corresponds to the physical quantity, electric field intensity or magnetic field intensity, and the imaginary part serves to keep track of the phase information. Now, in terms of the 2x2 matrix version of Euler's formula, both the forward diagonal and the backward diagonal, the cosine and sine terms have to keep track of the phase. And so I don't really agree with this logic here. And so then we go on to say, however, when deriving the final forms of Maxwell's equations in terms of the physical quantities, we typically focus on the real parts of these complex quantities because they represent the observables, the physical quantities. And so I don't agree with the statement either, because in my mind, the 2x2 matrix, the complex 2x2 matrix is one thing. It is not two things. It is not something that's real and something that's imaginary. The whole thing is real, and both the forward diagonal and the backward diagonal are required to get sensible results. And so finally it says, in essence, while complex numbers are useful for their mathematical formalism and understanding the behavior of EM waves, the final equations are expressed in terms of real quantities because those physical quantities are measurable quantities. Therefore, the imaginary components of the complex numbers are often ignored in the final forms of Maxwell's equations. Now, I personally don't think it's a good idea to ignore the imaginary component of the complex number. In the 2x2 matrix form, it makes it very clear that the forward diagonal and the backward diagonal both play a role in the observables, and so when you ignore one or over the other, then you are going to possibly get interpretations that are nonsensical. So in my code, you can see that in order to get the electro version, the vertically polarized version of the electromagnetic wave, or the component, I should say, of the electromagnetic wave, that I had to set the backward diagonal equal to 0. And then you will also see that in order to get the horizontally the horizontally polarized magneto component of the electromagnetic wave, that I had to set the cosine equal to 0. Okay, so basically we had to set the cosine, the forward diagonal here and here, equal to 0. Okay, and so we also had to add a phase shift to the blue wave to get them in phase. And so technically we're adding the phase shift to the cosine term, and we're adding the phase shift to the sine term in order to get them to be in phase in time. Okay, so but regardless of the fact that I've been able to get this to work, I'm still not sure it's the right thing to do. I'm still not sure that it is a good idea to ignore either the forward diagonal or the backward diagonal of the beautiful matrix of Euler's 2x2 matrix. I think that setting one or the other to 0 is going to lead to strange and nonsensical interpretations of the plane wave equation. So in other words, what I'm trying to say is I don't believe that the plane wave I don't believe that electromagnetic waves are plane waves necessarily. Okay, I believe that they are helix waves, elliptical waves, and if the wave is linearly polarized, I believe it is linearly polarized on a diagonal like that, not vertically and horizontally. In this implementation of the plane wave, both the cosine and the sine have a phase, and the sine wave just has a phase offset. So I'm not setting either the forward diagonal or the backward diagonal to 0 in the diagonal version. Okay, so in the linear polarization or elliptical polarizations, okay, all I'm doing is adding a phase offset to the sine and or to the cosine function. And so I think that light maybe does do this. Okay, I think it does do this, but I think, and I'm not ignoring either the real or the imaginary in this case. Okay, in this case, I can still get a plane wave, but I am not ignoring the real or the imaginary component. I'm still getting something that looks like a plane wave, so I'm not saying that plane waves don't exist. What I'm saying is the plane wave derivation that Maxwell did and others did after him by ignoring the real component and or the imaginary component and getting the vertically and or horizontally polarized waves is a little misleading and maybe even incorrect. And this may also be the reason why we need to do things quantum mechanically, because by ignoring the imaginary component of the 2x2 matrix, we are literally throwing the baby out with the bathwater. When you throw the baby out with the bathwater, then you're just guessing. Okay, you're just guessing, and that is what we refer to as probability distribution. And so when you throw the baby out with the bathwater, all you're left with probabilities. And so I prefer to start with the helix wave with circular polarization and go to elliptical polarization. We know these polarization modes exist, and to the linear polarization using the method of changing the offset of either the sine or the cosine term in the 2x2 matrix. And that way we're always using Euler's formula, we're always using the 2x2 matrix. We're not hacking out the forward diagonal or the backward diagonal arbitrarily. This is a beautiful solution. This is without doing any calculus at all. I'm able to I'm able to generate and visualize a planar wave, an elliptically polarized wave, and a circular polarized wave, all in one tiny piece of software, which I am going to package up and make sure that you have access to. So I'm going to give you access to this code, and you're going to be able to go through it and replicate all of the things that I did in this video.